Today we're going to look at the last and lecture 4 and the last lecture for chapter number 2. And our learning goals for today is to understand freefall motion, recognize the acceleration due to gravity in free fall, apply kinematic equations on a free fall problems. So we're going to look at freely falling bodies, and free fall here means something that you do not see any forces basically acting on it. So if you want to move anything, you have to push or pull on it to move it. But when you drop things, they actually fall on their own toward the surface of the earth. And that's why we don't see anything pulling them down to the ground, and that's why we say free fall. So that's basically what free fall is. And we say that this basically happening under the influence of gravity. So gravity is causing that. So if you look at the image that we have here, you drop a ball and the ball is coming down. Now in this cartoon here, they tell you that delta t between these images is the same. But you can see that if you look at delta y, which is the change in displacement, you will see it's getting bigger. And you all know that we discussed the Vx as delta, or the average, when we talked about Vf dash x, and we said that delta x over delta t. Here we can change delta x by delta y, and whenever this becomes bigger in the same time interval, you know that this is basically going to be different, and that's why we say the object will be speeding up. So that's one thing that you have to keep here in mind. And we say that the velocity is going to change over time. And this is what we want to address today. So this is basically what we want to look at today. Now, in the last lecture, we developed a set of equations, and these sets of equations were developed under one condition, and that condition was Ax is constant. So what happens when we choose the acceleration to be constant? We derived an equation describing velocity as a function of time, and we said Vx is equal to V0x plus Axt. X here denotes that it is the x component of the velocity, or in the case of A, it is the x component of the acceleration. Later in chapter number 3, we'll deal with the x, y, and z components. But this is only 1D equations. And the 0 here meaning at t is equal to 0. That means at the start when you start measuring time. So this first equation here gave us the velocity as a function of time along the x-axis. The second equation here, x minus x0, equals to v0xt plus 1/2 axt squared. And this basically gave us the position as a function of time. x0 here, that means the position at t is equal to 0. And v0x here, that means the x component of the velocity at time t equal to 0. And then we have a third equation, which basically relates velocity and position, which is Vx squared equal to V0x squared plus 2ax x minus x0. So these three equations here we derived in the last lecture under one condition, that the acceleration is constant, and they describe the kinematic for us along one dimension. Now, what we're going to look at today, we're going to look at free fall. And the free fall happens under the action of a gravity. So the acceleration is due to gravity, because you can see that if you drop something, the speed will increase. So you must have an acceleration. And this is what we call the acceleration due to gravity. Near the surface of the Earth, this acceleration due to gravity can be considered as constant. So we can use these sets of equations here that we derived under constant acceleration. However, the magnitude of this acceleration due to gravity is 9.8 meters per second squared. So what we're going to do with these equations here, we're going to change x into y. Of course, that means the ax will be changed into ay. So the ay will be our acceleration along the y direction, because we're looking at free fall vertical to the surface of the Earth, and we're going to use this vertical as being the y component in our case here. So now the ay here, the gravity will be pulling toward the surface of the Earth. And we'll consider going up above the surface of the Earth as being positive, and coming down toward the surface of the Earth as negative. So our ay here will equal to minus g. But g is equal to 9.8 meters per second squared. So before we start, I know that in high school, sometimes they tell you if you're going up, take g is being 9.8. If you're going down, take g minus 9.8. They always, in here, I don't want you to do that. Ay equal to minus g, and g is equal to 9.8 meters per second squared. Don't say g is equal to minus plus. No, g is 9.8 meters per second squared. Your ay now is equal to minus g. So if I come to my set of equations, and now I want to change the x into y, where I'm going to consider the y direction here is the vertical to the surface of the Earth. So the Vx, I'll change it into Vy. And the Vx, the V0x, I'll change it into V0y. And the Ax, I'll change it into Ay, but the Ay is equal to minus g, and that's why here I have Vy equal to V0y minus gt. And similarly, when I look at the position in the vertical direction, which we call it y here, or we choose y to represent the vertical to the surface of the Earth. So it's y minus y0 equal to v0yt minus 1/2 gt squared. And y squared equal to v0y squared minus 2g times y minus y0. You notice in this equation here, I'm not using ay, like in this equation here where we use ax. We already replaced the ay with minus g. And the value of g, when you use these equations, it's equal to 9.8 meters per second squared. I don't want you to say, oh, is it minus? No, g is equal to 9.8 meters per second squared. And that's what you put in these equations. And these equations later on, as we'll do some examples, they will take care of the whole trip for you. So these are the set of equations that can describe the motion in free fall, which is one-dimensional in this case, vertical to the surface of the Earth, under the action of gravity. Well, we'll try to always, when we start from t equal to 0, we say that y0 is equal to 0. Not necessarily, but in most cases, we always do that. So at t is equal to 0, you can choose your initial position, or y0 is equal to 0. Then you will have an initial velocity. Now, this is equal to what? It depends on your situation. If you're dropping something, then the v0y will equal to 0. That's if you just drop something. If you throw something downward, well, it's not, you're giving it some velocity now, so your v0y will be negative because you're moving, and we told you down is negative for us along the y-axis. And if you throw something up, you may want things to go up. And the only way that they can go up, if you basically throw them up. You cannot drop them up. You can drop things to go down, but you cannot drop things to go up. You really have to throw them up. And in that case, your v0y is what is positive. Are we clear on all of these? So we have equations to describe free fall. One is velocity as a function of time. One is position as a function of time. And one basically put the relation between velocity and position. Okay. Is this clear? So these are basically now our kinematic equations. Now we state here, question, is the acceleration 0 at the highest point? Because your experience, if you throw something up, you will find that it will go to a maximum height and then it drops back. And the logic that you always go with is when you throw something up, gravity is pulling down. So it will slow the object till it gets to the highest point at which the velocity will be 0, and then it drops back. That's if we're talking about only in one dimension. Okay. And many people always under the impression, if your velocity is 0, well, do you have acceleration? And yes, you do have acceleration. The gravity is not going to change. So even if you get at the highest point, and your y component of the velocity is 0, your acceleration due to gravity, which is pointing down toward the surface of the Earth, is not going to be 0. So for example, as we did in the previous lectures, we always also looked at a position time graph, velocity time graph. So if we look at a position, and here it is y, because we are considering the vertical above the surface of the Earth is y, and the units for it is meters. And on the x-axis here, we have time, and the units for time is seconds. That's why we have a bracket here and seconds. And if you look at your axis, the y can have positive values and negative values, but your time can have only positive values, because we always say that t is greater than 0. So if you plot your position as a function of time, and you already have the equation for the position where we say y minus y0 equal to the v0 yt minus 1/2 gt squared. That's our equation that describes the motion along the y direction under the action of gravity. Now, as I told you, you can always choose at t equal to 0, your y0 is equal to 0, but the v0y, that's basically a choice. Are you dropping, are you throwing up, or you're throwing down? So you have to be careful with that. So in this situation here, your y0 is 0, and you will get to a maximum height, and then after that, you will be moving downwards. So as you can see, you're starting from 0, and your y is positive. You will get to a maximum value, and then it will decrease. Now, when your y is decreasing, it's not negative yet. It's still positive, but it's decreasing. And then below the 0, it will go what? It will become negative. So you have to also be aware of this. Now, in this situation that we have here, if you're basically looking at this, now the maximum height was achieved at t is equal to 1.53 seconds. And you get a parabola like this. Now you can basically come here and you say, I want to look at my velocity time graph. So on the y-axis here, you have your Vy, and the units are meters per second. You have, on the x-axis, time, which measured in units of seconds. Your Vy can have positive values and negative values, but the time can only have positive values. And what you see now here, you're going to plot your velocity as a function of time, which is Vy equal to the V0y minus gt. And that's the equation that you have here. In this situation here, it happens that your initial velocity is about 15 meters per second. So it's a positive x component of the velocity. That means you're throwing something up. And that's why if you go back here, it's going up, and then it reaches the maximum height and then falls down. So in this particular situation here, you're basically having positive initial speed, initial velocity, and that's why is basically you're throwing something up. You know that at the maximum height, this velocity is going to equal to 0, and that's why from the plot here, you will find out that at 1.53 seconds, V here is equal to 0, which is the maximum height here. And this is now what happens that your y component of the velocity is equal to 0 at the maximum height. You can also, by the way, have another plot here, okay, which is a meters per second squared versus t in seconds. But of course, this is your g here is constant, and it has a value of minus 9.8 meters per second squared. So you can basically say that your g is somewhere here. It's a constant value. So that's basically now the three. The first is position time graph. The second here is velocity time graph, and that's the equation that describes that. Vy is equal to V0y minus the gt. So you're starting from 15, and as the time passes, it will become less and less till it becomes 0, and it goes down. And it's linear in t. Here you have t squared, and that's why you have a parabola. When it comes to a is a constant value. So here, in this situation here, you will say it's minus 9.8 meters per second squared. So that's in terms of the equations, okay? And this is basically in terms of the position time graph or velocity time graph. Is this clear? Is this clear? So now, like what we did, we basically started from position, then we came to average velocity, then instantaneous velocity, and then we dealt with average acceleration, and then instantaneous acceleration, and then we came to if my acceleration is constant, and in that case the instantaneous and the average acceleration are equal, and we developed the set of equations that I presented in the first slide along the x-axis, and then today we just shifted that to the y-axis, and we said that the y is equal to minus g, where g is equal to 9.8 meters per second squared. And you can also have a position time graph or velocity time graph. Your acceleration time graph is just basically going to give you a constant value because your acceleration is constant. Now, we have to apply these. So we're going to look at some examples. And the first example that we have here, it tells you that a 1 dirham coin is dropped from the Pisa Tower and falls freely from rest. So that's where you're basically throwing the dirham, or you're dropping the dirham. Right away, you know, when you drop something, your initial velocity is going to be 0. And they ask you here, find after 2 seconds, they want the position and they want the velocity. So as I told you, you can always, at t is equal to 0, you can choose your y0 is equal to 0, and your vy0, now it depends. Are you dropping, or you throwing down, or you're throwing up? In this situation here, you're dropping. So this is going to equal to what? Equal to 0. And they ask you, can you give me the position and the velocity after 2 seconds? Now, the equation for our position is y minus y0 equals v0yt minus 1/2 gt squared. Your y0 is equal to 0. Your v0y is equal to 0 because you're dropping things. So you end up with minus 1/2 gt squared. So it's minus 1/2 times 9.8 times 2 squared, and that gives you minus 19.6 meters. Now, again, some people you say, well, what do you mean by minus? Okay, because in many cases, things are measured from the ground. And sometimes people use the ground as y equal to 0. Well, in this situation here, we chose y0 to be on the top here. So this is the point when it comes here, which is basically, I don't know where, at 2, somewhere in the middle, it's equal to minus 19 meters. That means below your starting point, that t is equal to 0. Now, velocity after 2 seconds, it is vy is equal to v0y minus g t. The vy0 is equal to 0, and of course, minus 9.8 times 2, it gives you minus 19.6 meters per second. Now, the units here is meter, the units here are meters per second. The numbers just happen to be the same, but that's not necessarily the case. Okay. So that's after 2 seconds. So you look at your situation and you make use out of your equations. Is this clear? Now, this is basically how you apply your equations. Now, the example after that, we have an example here. And they tell you in this example, you throw a ball with an upward speed of 15 meters per second from a roof of a building. On its way down, it just misses the roof. And they tell you find the ball's position and velocity t 1 seconds and t equals 4 seconds. Now you throw something up and it comes down. When they say it just misses here, they're just telling you that it is one-dimensional motion. They want you to consider here a one-dimensional motion. So you throw something up and it comes down. Okay. So we can consider one-dimensional motion here. Now they tell you you're throwing something up with speed. Now remember what I told you about speed and velocity. Now in this situation here, your velocity will equal to the absolute value of your speed will equal to the absolute value of your velocity. So Vy here is a velocity. V here is speed. So if I put here 0 and 0 here, that means my initial speed equals the absolute value of the initial speed along the y direction. And it's given here as 15 meters per second. So if I want to look at my situation here, I will say that t equal to 0, y0 is equal to 0. I can choose that, and my v0y will equal to 15 meters per second because you're throwing up the ball. So basically, it's a positive value. And they ask me after 1 second and 4 seconds. So if I want to look at my position, after 1 second, the equation is y minus y0 equals to v0 yt minus 1/2 gt squared. Your y0 is 0, the vy0 is 15, your time is 1 second, so it is 15 times 1 minus 1/2, 9.8 times 1 squared, and this gives you 10.1 meters. So after 1 second, you are at 10.1 meters. That means you're above the building, above the roof, okay, of the building. Now, if you want to decide on your velocity, Vy is equal to v0y minus gt. Your v0y is 15, g is 9.8, and t is 1 second, and you get 5.2 meters per second, which means your Vy, your velocity, is positive. That means you're still moving up, but of course less than 15 meters per second, the starting, and you would expect that. At 4 seconds now, you're going to use the equation for the position, but for the time, you're going to substitute in 4. So it's 4 for t, 4 squared for t, and it gives you here minus 18.4 meters. So after 4 seconds, you are 18.4 meters below the roof of the building. That means you're moving downwards now, below that point here. And your Vy will 15 minus 9.8 times 4, and it gives you minus 24.2 meters per second. That means now your velocity is in the negative direction. Now, there's always, probably you did this in school, you look at the motion while you're going up and you look at the motion while you're coming down. Don't do that. These equations here, either for position or for velocity, take care of the whole trip for you. As I told you, ay is equal to minus g, and g is equal to 9.8, and that's what we put here in the equation. So it took care of for the whole trip for me. After 1 second, I'm still going up. After 4 seconds, I'm coming down. So I don't want to. Now you can tell me that, yes, you are below the roof, you're above the roof, you can, but these equations will take care of the whole trip for you. Is this point clear? Now, we're going to continue with the same example, but in this example here, they ask you the ball's velocity when it is at 5 meters above the roof. You know that in the previous example, 1 second you were at 10.1 meters above the roof. Now, you know that 5 meters will be less than 1 second in this case. But you know one thing, that you're going to go up and come down. So you're going to be at 5 meters above the roof of your building while you're going up and while you're coming down. And what they ask here is they want the velocity at these two different, at the same position, but while you're going up and while you're coming down. Now, your Vy initial is 15, and your Y initial is 0. That's at t equal to 0. Now, you're going to use the equation that relates both velocity and position. Vy squared equal to V0 squared minus 2g y minus y0. Your Vy squared is what you're interested in. Now, the V0 squared, it's 15 squared, minus 2 times 9.8. And the position of y that they want is 5, which is positive 5. And your initial is 0. 15 squared is 225. 2 times 9.8 times 5 is 98. So you get 225 minus 98 gives you 127 meters squared per second squared. Now they want V. So you're going to take the square root of V. And whenever you take a square root, you have to take the plus and minus. So it is a plus or minus square root of 127. And this will give you a plus or minus 11.2 meters per second. The plus is while you are going up, and the down while you are coming on, the negative while you're coming down. So at 5 meters above the building, not at the same time, at different times, while you're going up, your velocity is 11.2 meters per second. While you're coming down, sometime later, it is minus 11.2 meters per second. That's why I told you these equations take care of the whole trip for you. Now, I wanted to keep one thing in mind. When we dealt in chapter number 1, and we dealt with vectors, and when we never wanted to get the magnitude of the vector, we always took the positive root, because the magnitude should be positive. Okay? But in this situation here, you have to be careful. Whenever you take the square root of anything, you always look at the positive and negative. And positive here means while you're going up, and negative means while you are coming down. And the equation takes care for the trip for you. So you don't have to go and look at the time that you are at 5 meters while you are going up, and then you calculate the velocity there. You can do that, and you look at the time when at 5 meters coming down, and you calculate. It will take a long time, but these equations take they work for the whole trip, so you can do them in one step like this. Is this clear? Is this clear? Now, we're still with the same example, but in C here, they ask you about the maximum height. Now, usually, we going to use H for height. Okay. So we can look at the equation that relates velocity and position, Vy squared equal to V0 y squared minus 2Gy minus Y0. And we know that at the highest point, which is the maximum height, my Vy is equal to 0. So if I put Vy is equal to 0, and that only happens when y is equal to the maximum height. And that's why we put h here for y. And of course, the Vy initial is 15 squared, and the y0 is equal to 0. So 15 squared is 225 minus 2 times 9.8, which will be 19.6 times h. Okay. So you can take this to the other side. So h will equal 225 divided by 19.6, and you get 11.5 meters. So the maximum height that you can achieve here is 11.5 meters. Now we can ask you another question. Okay, the time at the maximum height. Okay. How much time? You can use Vy equal to V0y minus GT, and you know that the Vy is equal to 0 at the maximum height, and from that one you can basically calculate the time to reach the maximum height. In D, they ask you the ball's acceleration when it is at the maximum height. I told you that if an object in free fall, you throw something, that's it, it's out of your hand, you're no longer in control. So it's under the action of gravity, which means the acceleration at the maximum height, which is ay, will equal to minus g, which is equal to minus 9.8 meters per second squared. That's your acceleration here. There is another way that you can say, well, it is equal to 9.8 meters per second squared downward. But that's basically the way probably you're going to use, since you define where your y equal to 0. So the kinematic equations. Any questions on this one? Okay, the kinematic equations that we derived here, Vy equal to V0y minus GT, y minus Y0 equal to V0yt minus 1/2 GT squared, Vy squared equal to V0 squared minus 2G times y minus y naught. Okay, that's it. The minus is there because we said that ay is equal to minus. That's it. G is equal to 9.8. You don't put the g is equal to minus, plus, no, g is equal to 9.8, always in this equation. And these equations take care of the whole trip for you. All right then. Let's deal with some questions here. And the first question that we have here, the position of an object moving along the x-axis is given by this equation here, where x is equal to 5 meters plus 4 meters per second times t minus 2 meters per second squared t squared. Now, this you can basically, along the x-axis, you can say that x is equal to x0 plus v0 xt plus 1/2 ax t squared. So from this equation, you can say that your x0 is equal to 0. The v0x will equal to 4. And your ax here will equal to minus 4 meters per second squared, because you have 1/2 here, but here you have minus 2. So your acceleration must be in the negative direction, and it's equal to -4. That's why when you multiply it by half, you get this. So that's your equation here. Now they want you to represent this graphically with an xt graph. Now in all these graphs, sorry, your v initial x initial here should be 5 meters, okay, and this is 4 meters per second, okay. So when you look at this, you know that at t is equal to 0, your x must equal to 5. So this one here does not going to do it. This one is okay. This one is okay. This one, x is negative. This one, x is equal to 0. So your answer is between B and C. But if you look at this equation, that resembles to what when we looked at things that when you throw something else on the Freefall, so it will go to a maximum height, then it drops back. So yes, it will start from a 5. It will go to a maximum value, then it drops back. So the answer here is what? The answer is C. Is this clear? Now here, they give you the same equation, and they want a Vx graph to represent this. Now, you know that your Vx, it's dx by dt. And if you do that, the 5 here will give you 0 because it doesn't have any. So the Vx here, if you take the differentiation of d by dt, and here you're going to take d by dt. So the dx by dt will give you Vx. Now the d5 by dt will give you 0. And this one will give you 4 plus 4. And this will give you 2t. So we'll get here minus 4t. So that's your Vx now. Now, this will be the V0x, which will equal to 4. And this is now, it's going to be your acceleration, and we already talked about this should equal to -4. So when you want to look at a Vx time graph, you want to start from a positive velocity, but because you have a negative acceleration here, it will continue being positive, but then it will become 0 and it will go to the negative side. This one will start from a negative velocity, so that's wrong. This one from 0, that's wrong. This one from, it's wrong. So you're between C and B. Okay, you're between C and A. But A tells you that your velocity is going to be continuously increasing, but you have a -4 here. So the right answer here is going to be C, where you start from a positive value, you will get to a point where it becomes 0, and then it will be basically going in the negative direction. Is this clear here? That's basically similar to the Freefall equations. In this question here, if you toss a ball upward with a certain initial speed, it falls freely and reaches a maximum height h. By what factor must you increase the initial speed of the ball for it to reach a maximum height of 3h? So initially, you want to go to h, then you want to go to 3h. And you're throwing from here with, let's say, V0y. And you're going to throw even here with V0y, but let's call this 1 and this is 2. So by how much factor should I do it here to reach the 3h? You know that your equation Vy is equal to V0y, and here minus 2g times y minus y0. You choose your y is equal to 0, and of course the maximum will be h. That's why we do have 2gh. At the maximum height, your Vy is equal to 0. So you can take this to the other side with a positive. So that's why you have the V01, and we're just taking the speed here, should equal to the positive value. When you throw something up, it's going to be positive value. So I drop the y here, and we say that the V1, and they ask here initial speed. And you know, as I told you, that the V should equal to the absolute value of Vy in this case. So the V0 should equal to the absolute value of Vy0. And if we want to put 1 here, so it will be just the V0 at the case 1. So here it will equal to square root of 2gh. Now in the second situation, I will do the same thing. It is the same situation. It's V02, which is the speed. In case 2, it will be equal to square root of 2gh2, but h2 is equal to 3h. And if you do that, it will give you square root of 2gh. And if you do that, the ratio will be root 3. And that's why the answer here is A. Is this clear? So that's basically how you can manipulate these equations to get your answers. In this problem here, it is combining two things. It's combining one-dimensional motion along the x-axis for professor and a free fall along one dimension for an egg. So you are on the roof of a physics building, which is 46 meters above the ground. Your physics professor, who's 1.8 meter tall, is walking alongside the building at a constant speed of 1.2 meters per second. So he's moving with constant speed. That doesn't mean he doesn't have an acceleration. If you wish to drop an egg on your professor's head, how far from the building should the professor be when you release the egg? Assume that the egg is in free fall. So the professor is trying to walk into the building. You are on the top and you're trying to drop an egg. Actually, you have three scenarios here. Either the egg will fall in front of the professor before he walks into the building, or if it drops on his head, or it will drop after he walks into the building. So it all depends on your timing. If you want to egg basically drop on his head. Now remember what we told you, that at t is equal to 0, you always choose your y is equal to 0. But you have two situations here. So we chose the y equal to 0 at the ground level here, which we can call the x-axis for the professor. So at this point here, your y initial will be minus 46 meters. And the head of the professor here is 1.8 meters. So the egg, it should fall on his head. So I'm looking at y here, which is equal to, it's not minus, it's 46, because that's, so it's equal to 46 meters here. And the y here is equal to 1.8 meters. So if we use the equation for the position where we say y is equal to y naught, y0 equal to v0y minus 1/2 gt squared, your final y is 1.8, your initial y is 46, so 1.8 minus 46. The vy0 is 0 because you're dropping things, so that's equal to 0. Minus 1/2 times 9.8 times t squared. Now you can multiply this with a minus to make it positive. Of course, you have to multiply this with a minus, so you will get 46 minus 1.8 equals to, so from this equation here, you will get 46 minus 1.8 will equal to 1/2 times 9.8 will give you 4.9 t squared. So the t here is going to be positive value. So it will be the square root of 46 minus 1.8 divided by 4.9. So here it is 4.9. That roughly is going to give you 3 seconds. So the time for the egg to fall from a height of 46 meters above the ground to a height of 1.8 meters above the ground requires about 3 seconds. Now you turn to the professor, and he's moving along the x-axis, and you know that x equal to x naught plus v x naught t plus 1/2 ax t squared. But they tell you he's moving with constant speed, so he has no acceleration here. And he can choose the x naught for him equal to 0. So his x here will equal to the v0 times t, vx here. And it's equal to 1.2. So if you put the time of 3 seconds here, then of course that will give you a distance of 3.6 meters. Well, if you do it carefully, you may get something smaller a little bit, but roughly speaking, we say 3.6 meters here. So if you drop the egg when the professor is 3.6 meters away, well, when he gets to the door of the building, the egg will be on top of his head. So in this example here, I just want to bring one point where you choose the y to be equal to 0. We always do it at when t is equal to 0. But in this case, you have a professor walking here. So you really have to consider y equal to 0 at the ground or the surface of the earth. Is this clear? Any question on this? Any question? So what we've done in this lecture, we basically dealt with a free fall in one dimension with constant acceleration, and we took this acceleration due to gravity, and we said that it is ay is equal to minus g, and g is equal to 9.8 meters per second squared. G 9.8 meters per second squared. But in our equations, we used ay is equal to minus g. Then we basically looked at directions and magnitude of the acceleration, and then we dealt with kinematic equations in one dimension. Okay. Any questions on these? So today, yes, okay. Today we're only dealt with the motion in one dimension in a free fall. So to recap the whole chapter, we started from position. We said you start from a position, and we took that along the x-axis. So you can start from position 1 and you move to position 2, And we define the difference between these two positions as being delta x, where delta x is displacement, and which is x2 minus x1. Then we defined the rate at which this displacement can change. You can do that in different times. So we said that Vf along the x direction equals to delta x over delta t, which is x2 minus x1 over t2 minus t1. Now, sometimes we can write this brackets around Vx, which means the average velocity along the x direction. That's another way of writing this. But in the textbook, we write it Vf-x. We defined another quantity as well, which we call average speed. And we said that this should be the total distance over total time. And we said average velocity and average speed are not related at all. And we dealt with examples to state that. Now, when it comes to instantaneous velocity, and remember when we looked at an xt graph, you said you draw a line tangent to the point or at the time where you want to get your velocity, and you take the slope of that tangent. And we said this is in the limit as delta t goes to 0, delta x over delta t, which is dx by dt. And we said this is basically your instantaneous velocity. Then we said that your speed should equal to the absolute value of the velocity. That's why we're not having x here. Speed is a magnitude, does not have components, but it is the absolute value in this case for the Vx. Now in chapter number 3, we will talk about x component, y component, and z component. So that's what we did in the first lecture. Then the lecture after that, we extended the concept to changing the velocity, and we talked about AF along the x-axis, and I told you it can be written in this way as well. When you put these brackets around, it's also the average x component of the acceleration, which is delta Vx over delta t, which is V2x minus V1x over T2 minus T1. And the instantaneous acceleration, it's in the limit as delta t goes to 0, delta Vx over delta t, which is dVx by dt. And that's now the instantaneous acceleration, the average acceleration. Okay. Now you may write the acceleration as the absolute value of ax, and that means you're only taking the magnitude of the acceleration here. Now we developed a set of equations, and these set of equations were developed when ax is constant. Okay, we developed that Vx is equal to V0x plus axt, x minus x0 is equal to V0xt plus 1/2 axt squared, and the Vx squared is equal to V0x squared plus 2ax times x minus x0. But remember, we did that when ax is constant. Now you have here a square. So if you do a position time graph, you'll get a curve like this. If you want to do a VT graph, and this is basically the equation that you can use for your velocity as a function of time. And if you want to look at AT, since it's constant, it depends. Is it positive? Is it negative? So in this case, if it's positive, it will be constant above the t here, meaning positive. It is basically, it could be negative. So you'll have here your a and your t, but the value could be here. It depends on the value. And we use this equation to describe motion along in a straight line or in one dimension along the x-axis. And today we extended this for a free fall. And a free fall, all we did is basically we changed the x into y. So we change the AX into AY, and AY is equal to minus 9.8. We said that the AY is equal to minus G, and we said the G is equal to 9.8 meters per second squared. So all of the equations that were developed, we change the AX into AY. So you have Vy is equal to V0y minus G T. Y minus Y naught is equal to Vyt minus 1/2 GT squared. It should be AY here plus 1/2 AY, but the AY is equal to minus G. And Vy squared equal to V0y minus 2G times Y minus Y naught. And I told you that G always equals 9.8. Is this clear? Any question on this? Good.
Yes, doctor, I have a question.